Welcome to today's webinar with Dlubal software. My name is Wieland Götzler, and my colleague Andreas Niemeyer and me, we will show you simulation of air-inflated foil cushions in RFEM today. Let's take a look. Before we take a look at the content for today, I will show you how to ask questions and check some settings in your GoToWebinar. On the left side, you will see a panel. You can show and hide the panel with the left arrow on the upper left part. You can check your audio settings when you click on the sound check button over there, and you can ask short questions in the bottom of the panel. With that said, we will take a look at today's content for the webinar. At first, my colleague Andreas Niemeyer will show you some news about RF form finding and RF cutting patterns. And in the second part of the webinar, I will show you how to model and analyze an air-inflated foil cushion in RFEM. And with that said, I will just hand over to my colleague Andreas, who will give you some news about the form finding.
So, hello. As introduced, I will give you now a short overview about the latest developments of our form finding and cutting patterns, and I start with the latest 3 items in form finding. And as you see on my slide here, we introduced in the last time a form finding assumption for compression loaded models. You can now find shapes for such anticlinal arch roofs, and because this sounds in first instance quite complex, I want to give you a short inspiration how you can do this with our program. For this, I jump in our RFEM, where it is here, and you see this is a typical initial model for such a compression loaded form finding input. This should represent finally a bridge. For finding this bridge shape, you define here a flat concrete slab. You see it's a concrete slab. If I open the properties, we have a thickness, we have a material, we have in background some form finding settings. Means we have a form finding assumption, we have defined a force and a force ratio minus 60 kilonewton per meter and minus 70 kilonewton per meter in y direction, and for the free region where you can finally go through the bridge, we have defined some beams, and these beams have also a form finding setting in background where I have defined I finally want to have a beam with length 35 meters. Sounds fantastic how to envelope from such a flat model bridge, but after running the form finding process with considering the quasi-permanent load, for example here self-weight, you will find a shape, and I ran now the process. You see he will start iterating, the deflection will be increased. Finally, I expect that I get a sag of 8.5 meter roundabout. You see the peak was reached here, and we converged to this 8.6 meters. And now this slab is lifted to overtake the quasi-permanent load as compression down to the supports. This is a support force, what you can see here. And of course, this shape is loaded with compression forces. You can display it here. And the shape, what our program envelopes here, looks like this. If I display the C coordinate, you can go through the bridge, and here you can go over the bridge. And to see that this example is not the idea from myself, I found one possible or customer projects what fits quite good to this example. And if I open here our website, www.dlubal.com, you will find below download and info a customer project, not the latest, but here from March, customer projects from our customer Technische University of Vienna. They took care about a form finding issue to find a wildlife bridge shape over a highway, and they did a similar assumption but manually. So of course they model also the foundation, but the topic here was also to find a shape which is under compression and fits to some settings according form finding idea. So this was my first topic I want to show you. The next topic what we introduced in our program was advanced projection method. At first, what could be done with this method, but I want to show you the details by modeling such a conical tent shape. For this, I going in our program. We open a new sheet, T1, for example, 3D model, upwards direction. I open a template with textile materials and activate my form finding and cutting pattern modules. So we override the existing. And for such a tent model, you don't need a lot of input, but we need one line, for example. It's running here from this points, and now we let rotate this line around the z-axis. For this I use a rotated surface. Material we can define directly. For example, a Ferrari material is related thickness of 1 millimeter, and we define orthotropic membrane finite element for this. The membrane should run around 360 degrees, and the axis is 0, 0, 0 and 0, 0, 1. And after picking the line, I get this as initial shape. For the process, I need some boundary conditions. I define it here on bottom and on top. And finally, we have to align the warp and weft directions. Here I use the surface setting axis, where I say the axis X should be oriented to the center line. Here I use the same unit vector and confirm it. Now we can apply a force ratio, and as we know, for such conical tents we have a quite typical issue that we cannot hold the pre-stresses around the tent. We have to modify the form finding process, and therefore I fix it on the XY plane of this conical tent and allow it only to move upwards and downwards. And now I can define here a force ratio. Before it was only possible to work with ratios 2:1. Now I can change it, for example 10:1. This results finally a shape which is close to this origin shape. What means we have at least finally here no big sag if we scale it to 1, what represents the form finding shape. It's close to this origin. If I change it, and this is quite new and was not possible before, I can change it 1 to 10, that we have a quite high force in tangential direction. We can produce now any sag we want or expect for such type of models. You see now here the sag is much bigger, and This is quite helpful if you want to search here models which fits to this topic. So, and then I coming to the last feature of form finding, and this is quite near practice. What means that you can use this geometric what we envelope in our calculation core, that you get it for example in AutoCAD, or that you can export it into a DXF file. And now we open this interface not only to export the mesh from form findings and also the deflection after loading this shape. I want to show you because it's quite easy. I'm going back to RFEM where we are here, and that we have a loaded shape. We apply, for example, here a load case snow without self-weight, of course, and here surface load on true area with -1 kilonewton per square meter, what is in fact quite high here for a membrane model. And if we calculate the shape of this load case, we get a typical sombrero shape. It looks quite nice, but it scale up to 6. If I scale it to origin shape, it looks not so critical. But you see, this shape is from form finding process, and this shape below is after applying this snow load. And if you want to use this shape also in a CAD application, you can open, for example, in AutoCAD, empty sheet, go back to RFEM and say, please export me this shape to AutoCAD, activate here deform shape, and after confirming the programs communicate to each other and export the data. And when we change now to AutoCAD, you see you get here a circle, but it's more than a circle. It's our conical tent in 3D, and you see also here the difference between mesh and shape from after loading. You can display both, or let's deactivate the display of the origin shape and display only the loaded shape after applying the snow load. And of course you can shade it if you wish, or if you want to make a collision control. You have this data completely now available in AutoCAD and can make your drawings or what you need. And this leads me now to our next feature, what is now not below form findings and below the category cutting patterns. Here we introduced also some features in the last time, and one feature was the output of results after flattening. We think these results can help you for finding the right compensation. If you know which forces or strains a flattening process gives you in the element itself. To have an imagination how big and how this looks like, let's make a short cutting pattern definition in our conical tent. For this, we jump back to RFEM and apply here a section line. I define here my working plane in XY and introduce here a line cut via section. We define one cutting point in center, and the second here 45 degrees rotated outside the model. We say it should be a geodesic line with a direction vector in C. And after confirmation, we get this section line lying on the mesh. Of course, if you need more, pick it and rotate it around center, maybe 30 degrees with 11 pieces, and start the process. And you get these lines also around the tent. And these lines you see are lying on mesh. So, and now let's define one pattern for this calculation. I say new pattern, define here lines, what meets this pattern I want to analyze. So this first one without this origin line. The program is overtaking data into this flattening machine, let's say. And I have to say create, and now we have a first view of our pattern. It's already flattened, but it's only a preliminary shape. If you wish real dimension of it, you have to start the calculation. It's a second calculation on this initial calculation, what gives you an exact shape on basis of an energetical assumption. And here you get for all coordinates around and also the length and width of this pattern. And now additionally you get for this pattern also results. We can display it here for cutting pattern, activate it here. Of course you can display the flattening process. Yeah, you see now it's flattened on XY plane, and if I change scalation back to 0, it's on origin shape. And the strains you can also display it. You see here, if you press this pattern down to XY plane, you will activate the compression and tension stress in this pattern, and this will be displayed now directly in the model and could be used from you for finding the right compensation and so on. So as next, we coming to the next feature I want to show. Imagine you have to produce more than one pattern. For this, we have a pattern generator. It's placed below tools, generate cutting patterns from cells. This generator allows you to produce patterns from these section lines. Of course, you can define here some lines which should not be used. For example, this origin line is not interesting here. And after confirmation, you can envelope all patterns around these shapes. This, I think, is quite helpful to make in less time a lot of patterns. And now you can start give definitions what is weld and boundary line, and give extensions on it if you need it. So this should help you in this working process. And now I'm coming to the last feature. For this, let's have a look on this picture. It gives you a picture of our world map. And as we know, we are living on a globe. And if you want to display this map or this globe on a map, you have to flatten it. And to flatten such a model, you have to introduce cuts. Yeah? And this is one style to simulate such a map. And you can see the manufacturer of this map used cuts here in these directions. And now we use this as inspiration and also integrated cuts in our flattening process. And I tried to do the same. Therefore, let's go into RFEM, open a new file, and see this globe or hemisphere. Yeah? This is a half or a hemisphere, and you see I already introduced some lines in it. And if we mesh it, generate mesh, you see some lines of this cutting pattern definition. It looks like we have several cutting patterns, but in fact it's only one cutting pattern. You see, we have only one definition. And this pattern is running around this center circle and have cuts here in these regions. And these cuts are not closed, have here a small gap. So here it's stopped, and we cutting from top to center and from bottom to center. And if I run here this process, we get a shape. At first it looks quite strange, but let's see it with the escalation. At first we start here by 0. This is the hemisphere shape, and if I flatten it down to x, y, we have here this shape compared to this world map. So if you have to simulate during your flattening process also cuts, you can do it like this. It's only a line what you have to pick in the definition itself here. So now I'm coming to the end, and I want to give Wieland the control back.
All right, thank you very much, Andreas. I will try just to make a presenter to my screen. Yeah. Let's check the audience view. Now it should work. So that was quite impressive, I have to say, with the hemisphere and the cutting patterns. And I hope I can hold it up with my foil cushion now. Now it's getting a bit more practical in the program, or we will do a whole model in the form finding. And I want to show you how to define a foil cushion. So at first, of course, you hopefully all know it. I am starting with a new model general data. We want to use global z-axis upwards, and in the options dialog we activate the form finding. Okay, that's prepared. And before starting to model, I want to adapt some data units in decimal places. And I start with the model. We want to have the material properties in kilo-newton per square meter. In this case, we want to have the loading in Pascal, pressures Pascal, you can see over there, and the membrane forces to be with 2 decimal places. For the results, we want to check the deformations with centimeters displacements, and also the stresses in the solids we want to have as Pascal. All right. Actually, this example you will see in the following modeling process you will find in a practical book from Rosemarie Wagner, Bauen mit Seilen und Membranen. It's like building with ropes and membranes, and we will do a small comparison with this example in the webinar. So let's start to model. I will just define some basic structure of a rectangle of 12 meters to 4 meters. That's 5, that's 4 meters, and then we are done with a rectangle. Perfect. Before defining the foil, we have to define a new material. I guess on the left side you will see concrete and steel, which is not so useful for our cushion. So that's why I choose a new material from the database. No, actually I can just define it over here, and I will just name this like the membrane material. For the calculation, we want to have a material model of orthotropic elastic 2D, because it's for the surface, and a new dialog will pop up, and there we have to define a ENG modulus, shear modulus as well, and that's it. Okay. We don't have want to take the specific weight into account, and also terminal expansion is not interesting in this webinar. All right. Now we have the membrane over here. We will add some gas later, and we can just define a surface with insert model data. We want to have a surface, and there you will find B-spline. Okay. Select the material. B-spline is right, and the stiffness should be membrane orthotrophic. Okay. Now we will, we can just generate the surface, I guess. Okay. Okay, and select the boundary lines, and you can see that all the boundary lines are selected automatically, and it's already generated. With a right click, you will leave the dialog, and to define the pre-stresses for the form finding, we have to adapt the axis of the surface. And this is what you can do with the stiffness. First we have to define the axis, as I said. Therefore, we go to axis for input, and the axis x-axis should be parallel to the short line of the rectangle, which is line 4. Okay. Okay. And now we can define the pre-stresses of the form finding process by moving to this dialog. Stiffness, membrane orthotropic, you will find this edit button over here. And in the form finding part, you can define different pre-stress forces with the directions nx and ny. This is why we defined to be the x-axis to the parallel to the short boundary line of this rectangle. And we can define 1.56 kilonewton per meters for the warp, and for the weft we will define 0.75 kilonewton per meters. This should be okay. Thickness is 1 millimeter. Okay. And that's it. Okay. What we have to do to get the, not the initial shape for form finding, but for the surface, we have to shift these nodes. These nodes are part of the B-spline surface, and therefore I will just change the view in Z-axis, switch off the switch to wireframe display model, select all the nodes, right click, edit node, and there you can see all the nodes are in the selection. X and Y is different, of course, and we can easily change the Z-axis, Z coordinate to be 1.5 meters. So now it looks like this. No change at all, but when you switch on the solid display model, you can see that's already like 50% of the cushion. What we need to do is we need to mirror it somehow, and therefore just select everything, use the mirroring function over here on top. You will find mirror. We want to create a copy, of course, and we want to use not YZ plane, which would be problem. We want to mirror in XY plane. The mirroring plane is already defined with the origin of the grid, and now it still looks a bit the same. The nodes are actually on the bottom, and when you rotate, you will see, okay, looks quite good. So for the definition or for the calculation, we need, of course, some supports on the boundary lines, and because we just have 4 lines, I can easily select a hinged support type, press OK, and select everything in the structure, and all the lines are supported now. Okay. What is still missing is filling of this cushion. So at the moment it's just not inflated, there's no gas inside, and we need to define a solid inside in between these two surfaces. And to do this, we can easily use new solid over there. It's not filled with concrete, of course, and not filled with steel. That would be quite tough. We will just import from the material database, and you can choose gas as a category group, and we will have some dry air in between of the surfaces. Just select the boundary surfaces. If you choose autocomplete, it will just take all two surfaces into account to complete the solid. That's a quite good tool. If you have a more complicated shape, you can easily select all the boundary surfaces in just one click. Okay. Press OK, and the solid type, of course, is gas. That looks good. Let's check the dialog. You can define an initial atmospheric pressure over here, and you can define temperature. In this case, we just use 23 degree, but it's actually not part of our calculation now. Okay, that's already the whole modeling process, and we can start with the calculation part now. Therefore, I will just define a new load case. Right-click on the load case, new one. We want to be the load case 1 as the initial shape or initial condition of our form finding. Initial shape for form finding. Action category is important. You will choose form finding over here, and in this case we deactivate the self-weight. That's it. Okay. What we want to do now is we want to have we want to have a pressure in this volume of 300 Pascal, and this is what we can define with a solid load. And this you will find new surface load. No, that's not right. New solid load. Okay. Solid number 1, no, that's new solid load number 1. We want to have a gas, and we want to have a resulting overpressure of 300 Pascal over here. Just click OK. And because I choose graphically, I have to pick something in the graphic, and you will detect the solid with a node in the center of this solid. So this one, you get some information plus 300 Pascal. And that's it. We can just start the calculation, I guess, for the initial shape for form finding. Let's find out. All right, so now it looks like this. We will take a look at the contour lines in this area, and you will find the information in the panel. It's 39.96 centimeter of not a deformation, it's a contour line. That means it's like the Z coordinate. So the top of this cushion is about 40 centimeters in plus Z, and the bottom is minus 40 centimeters in Z-axis 2. And in the book I told you at the beginning, you will get also the initial shape of 40 centimeter. So it's exactly the same in the form finding process, which shows that we didn't do something wrong in the modeling of the materials and the model itself. So that looks quite promising. And in the next part, we want to define some more loads and compare the results with the book. So let's take a look in the data dialog. We will just use load cases, edit load cases. and we want to define a new load case, or can just copy that one, doesn't matter. And this load case should be, it's named open cushion with pressure and snow. So we will use snow loads as an action category and name it open cushion with pressure and snow. All right, okay. Now we are actually in the load case 2, open cushion, pressure and snow. What we want to define is a resulting overpressure of 600 Pascal now. Double click this one, change to 600. Okay. And to define the load case now, we will use the upper surface. Click on the new surface load. It is a projected load. You can see in the graphic what happens if you choose different categories of load, like related to local area coordinate system. We will define it for the wind loads later, but in this case we have snow, which is projected. Uniform load case is correct, and we want to use 0.52 kilonewton per square meter as the magnitude. If you use a positive value, then you would have an uplift snow, which is not correct. So in this case, we will define it with a minus, and this should be okay. Yeah, looks good in this case, and that's it. We can just run the calculation again and compare it with the results from literature. So now it's done. Contour lines shows us the coordinate of the surface again, and you will see 35.66 centimeters on top. That's the red one. And on the bottom, you will see about minus 43.37 centimeters. And the literature is telling us an analytic result of on the top surface of 35.6, which is really close to our results, and on the bottom 43.4. So very nice comparison with an example from the book. Let's also check the internal forces in the surface, and therefore I think it's a bit tough to compare it. No, it's fine. We can use NX to have the forces in local x-axis of the surface, and in the literature you will find 2.91 kilonewton per meters, and we have in our numeric solution we have 2.95. If you want to see the exact result in this surface, you could also use a section, what I want to show you in the next step. Section over here on the left side in the data navigator, right click, new section. Section name is, for example, we have just one section now, section 1. We want to have a projection in global Z on all the surfaces, or if you want just to check the top surfaces, top surface, you can easily select this one. Define the edge points of the section, which is the most important thing, I guess. We want to have a section in the middle of this, and with the object snap, it's useful and easy to define the section, and usually it's opening after pressing OK button. And you can easily define, for example, an X and Y to have a nice comparison of the X place. You can also switch off like the distribution of load we don't have. So basic internal forces on top, 0.55 kilonewton, like in the literature. Perfect. Okay. Can just close this one, and now we want to calculate a load case with a closed cushion. That means there is no, there's actually only the pre-stress from form finding process, and in practice there can be some like losses of pressure, and this is what we want to calculate in this next load case. We will just copy this one, rename it to closed cushion pressure plus snow. Okay, can easily remove this one. Okay, and just run the calculation again. Okay, check the contour lines first. The literature gives us an analytic solution of 35.7, which is quite close to our numeric solution. On the bottom is 43.2 centimeters. It's also nice. And check the normal forces on top. With the section, we can just press the OK button again. And X on top in the literature, it's 40.43 kilonewton per meters. And yeah, it's exactly the same, so quite satisfying. We can also check what's happening with the internal pressure now, because we don't have internal pressure like in the last load case. You can see over here that should be the resulting overpressure, but we don't have it in the next load case. So when we take a look at this one, you can choose solids, overpressure, and this is almost like 600, and it's in fact, yeah, when you have a closed cushion and you put some load on it, you will increase the overpressure inside the cushion, and that's plausible results here. Okay. For the next two load cases I want to calculate, I want to have some wind loads, as I told you in the beginning, and therefore we will just copy the open cushion again, copy the load case, pressure plus snow, and we have a pressure plus suction. Okay. Pre-stress is here, and let's change the definition of the load case to have action category wind. Okay. And of course you could, what I told you, that this is still the projected load from the snow, and we will just adapt it to local Z. And we have a suction load case, and this is 0.78. Okay. Perpendicular to the membrane, this is what you define over here with the local Z axis. Okay, that looks nice. And we want to have a pressure of 300 Pascal. Okay. Run the calculation again. Okay. Of course, because of the loading of the resulting overpressure, we have an overpressure of 300. This should be definitely the same. And let's compare the other results with the literature. We have a normal force on top, NX, membrane force of 4.82. Let's activate the normal force NX. What is this one? PZ. Again, we will just switch it off and use the NX force 4.82, which is perfect. And also check the contour lines of the process, which is 47.77 centimeters in our example of in our numeric solution, and in the literature you will find 47.6. So also quite nice comparison with the book. And yeah, for the last load case, let's remove the overpressure from the cushion and we will just copy the load case again, change to closed cushion, pressure plus suction. Yeah, still wind. Okay, so let's check the inner pressure of the solid, and yeah, we have just the overpressure of 7 kilonewton, and this is why it's like the opposite of the snow load case. Yeah, if you have a uplift wind load, that's the surface load we've defined in the last load case already, and you have no pressure or just the pressure inside the cushion and it's closed, then you will have they are acting against each other, and you will reduce the overpressure inside the cushion. So that's also quite plausible in this case. We can still compare the control lines in the literature. It's about 45 centimeters on top and on the bottom 34.8, and you can see in the panel that also the results of the control lines, the set coordinates of the cushion, they are matching quite nicely. And with that said, I'm done with this small comparison of a foil cushion in RFEM form finding calculation with a verification example of the book. I can just mention it again to you. Rosemarie Wagner, Bauen mit Seilen und Membran, Building with Ropes and Membranes. And I want to give you some more information you can see on our website. Today's webinar is of course recorded, and you can find it when you move to dlubal.com, support and learning. In the learning part, you will find webinars, and on the bottom left, you will see accomplished webinars. You can either watch on YouTube or just download the webinar from our website. And what I propose is just take a look at the download part, download today's the trial version and try the model of today with the form finding. If you find questions, just write us an email, call us, send a comment on YouTube, and we will get back on you. And thank you very much for your attention.